Hi, today I'm presenting my work on sampling uniform random networks with fixed degree sequences. Network analysis is widely used to study patterns of interactions in a variety of systems. For example, we can have a network of people talking to each other or a set of computers interconnected through a LAN. The food web can also be imagined as a network connecting species based on who feeds on whom. We could also imagine a network encoding the hiring of PhD graduates of one university as faculty in another, or we can even have brain networks where the components of the brain are interconnected based on their functionality. In mathematical terms, each interacting entity of a network is called a node, while the connection between a pair of nodes is called an edge. The number of connections a node has is called its degree, so the bottommost node here has degree 3. And a sequence of degrees of all nodes of a network is called the degree sequence of the network. Oftentimes, when analyzing patterns in networks, we come across the question of whether an observed pattern is really unusual or is it simply a consequence of the degrees alone. For example, consider a dataset of 4th grade students of a Dutch school. Here's a network where each node is a student and two students are connected if they give and receive emotional support, obtained from a survey that the students filled out. Now we want to know if the students have a gender preference in terms of who they reach out to for support. To evaluate that, we calculate the gender associativity of this network. This coefficient quantifies the extent to which nodes of the same gender connect with each other. That comes out to be 0.62. But we cannot really interpret this value because unless we have a baseline or a reference distribution to compare this value with, we won't know if this value is high or low. To get that reference set, we have to generate a set of networks with the same number of nodes, edges, and degrees as that of the original network, but where the nodes connect completely at random. If these networks, with randomized connections, have the same gender associativity as that of the original network, we would conclude that the observed pattern is just a consequence of the degrees. That is the number of connections each node has. Whereas, if the original network's gender associativity is much higher than the randomized networks, we conclude that the students indeed have a strong gender preference regarding who they share emotional support with. The problem of generating networks, also called graphs, with fixed degrees has been an open question for decades. In 2018, Fosdick et al. Proposed one of the best solutions known so far. In their method, two edges are chosen uniformly at random from the network, and then they are swapped in either of the two possible ways as shown. Note that by applying this swap, the degrees of the nodes stay the same, but their connections change. If we keep applying this swap repeatedly, we get a time series of graphs forming a Markov chain where all graphs have the same degree sequence as that of the starting graph G0. Now Fosdick et al. Defined the rules of this swap in a way that after a large number of swaps has been applied, this Markov chain will start sampling uniform random networks with a fixed degree sequence. But this solution is not complete, and here's why. First, how long the Markov chain needs to run before it converges, that is, it starts to sample graph uniformly, is not known. And second, consecutive graphs in this chain are highly correlated because they only differ by one swap. To be considered as uniform random networks, they should be structurally independent. It is not known how many swaps between two graphs in this Markov chain is enough to ensure that independence. So these are the two questions I solve in my project, thus offering one of the first practical solutions for sampling graphs with fixed degree sequences. So here's my solution. First, in order to track how the network structure changes from step to step as the swaps are applied, we need a value to monitor the chain. To do that, I convert the time series of the graphs to a scalar time series by calculating the degree associativity of each of the graphs. Using degree associativity to monitor the progression of the Markov chain is very inexpensive, which makes my method computationally very efficient. Here is an example of how the degree associativity of a given network is changing as the swaps are being applied. Notice that the value quickly moves away from an initial point and then it stabilizes. Now that I can track the Markov chain, I estimate the gap at which networks in this chain become structurally independent. Consider a list such that the consecutive values in this list are degree associativity values of networks that are eta swaps apart in the Markov chain. I calculate the correlation of this list with the lagged version of itself where the lag is 1. My goal here is to find the smallest gap, which I call eta naught, for which this lag 1 autocorrelation is not statistically significant. This is because if consecutive values in this list are statistically uncorrelated, it would mean that the eta number of swaps was enough to make the networks independent. I then apply this lag1 autocorrelation method on more than 500 real-world networks to obtain the sampling gap for each. This figure shows how the sampling gap varies as a function of number of edges on 8 different types of networks, depending on whether the network contains loops or parallel edges. The strong linear pattern between the sampling gap and the number of edges allows us to propose upper bounds, shown by the green lines. Thus, for any new network, we can automatically get the sampling gap from these upper bounds without even having to run the sampling gap experiment from scratch. Okay, now that I can estimate the sampling gap, I design a test for detecting when the Markov chain has run long enough that it has converged. That is, it has started sampling networks from the target uniform distribution. To do that, I use the TF-GLS test of stationarity, which is a statistical hypothesis test that detects whether the mean, the variance, and the autocovariance of a time series changes with time. Here's an illustration. I first run this test on an initial portion of the time series. If stationarity is not detected, I slide the window forward and I test again. And I keep sliding the window and testing for stationarity until stationarity is detected. That's the point where I claim convergence of the Markov chain. Lastly, I apply my method to real-world networks. Coming back to the emotional support network example, let's remind ourselves that we are interested in the question of whether the students have a gender-based preference for sharing emotional support. Using my method, I first generate a large set of networks with the same degree sequence as the shown network, but with completely randomized connections. The gray shaded portion of this figure shows the distribution of the gender associativity had the students connected uniformly at random, without any bias. We can clearly see that the observed associativity, shown by the yellow dashed line, is much higher than the reference set. Thus, we can conclude that there is evidence that the students in this network exhibit preference towards the same gender when giving and receiving emotional support. All our implementations are available as a Python package and have already been publicly used for network analysis. Thank you.